Look at the objects on this table: a glass of salt water, the air we breathe, a steel wrench, and a glass of milk. They all look perfectly uniform, but if you zoom in close enough, you'll find they play by completely different sets of rules. Our eyes are easily tricked. Just because a liquid or a piece of metal looks seamless doesn't mean it actually is. Many of the things we interact with daily are hiding microscopic divisions. A true solution is defined by its uniformity. It is a single phase of matter where every component is distributed evenly down to the scale of individual molecules. Every drop or sliver is identical to the rest. Every true solution requires exactly two roles. First, you have the solute, the substance that gets broken down and dissolved. Second, you have the solvent, the substance that does the dissolving. Usually, the solvent is whatever you have the most of. To figure out which of the items on our table are true solutions and which are elaborate illusions, we have to look past the surface and judge them by their hidden molecular mechanics. When you hear the word solution, you probably picture stirring a solid powder into a liquid. But solutions aren't limited to liquids. They occur in all three primary states of matter. Take the steel wrench. It is a solid solution, known as an alloy. Steel is an alloy where carbon solute slips into the gaps between iron solvent atoms. In salt water, active water molecules pull apart and scatter salt ions evenly. In air, oxygen diffuses seamlessly into the nitrogen solvent. Whether locked in a solid grid, flowing in a liquid, or drifting as a gas, the defining trait of a true solution is complete, invisible integration at the molecular level. Physical state is only part of the equation. If you pour two liquids together, like oil and water, and shake them vigorously, they won't automatically form a true solution. Water molecules are polar, with distinct positive and negative ends. They act like magnets, strongly attracting each other. Oil is nonpolar, lacking these poles. When mixed, water molecules pull tightly together, squeezing the oil into a separate layer. Now compare that to vinegar. Because vinegar is also a polar molecule, it shares that magnetic quality. When vinegar meets water, the two liquids strongly attract each other and mix perfectly into a uniform solution. You can stir a mixture all day, but if the underlying chemical polarity doesn't match, the molecules will refuse to bind together. Even if the polarity aligns, there is a physical limit to what a solvent can hold. When the particles of a substance are simply too massive to dissolve, you no longer have a solution. If you stir chalk dust into water, the water turns cloudy. This is called a suspension. The chalk particles are large and heavy. Gravity takes over, dragging them down until they settle in a layer at the bottom of the glass. There is a deceptive middle ground that mimics a true solution, while failing the molecular test. Chemists call this a colloid. Milk looks uniform, but microscopically, it's packed with massive fat globules. These globs are too small to sink like chalk, but too large to truly dissolve into the liquid. You can force ingredients into a temporary colloidal state. If you add dish soap to separated oil and water, the soap acts as a molecular bridge, grabbing both oil and water. This creates an emulsion, holding the oil droplets suspended. When a substance lacks the chemical compatibility to dissolve perfectly, its physical size dictates everything about how it behaves, turning what looks like a solution into a heavy suspension or a cloudy colloid. Looking back at the table, the salt water, the air, the steel wrench, and the milk, we can now categorize each one by the chemical laws that govern their structure. In the salt water, air, and steel, the components have merged into a single unified phase. But the milk is different. Its appearance is a byproduct of particle size, just as the separation of oil and water is a result of magnetic repulsion. Even true solutions have strict physical limits. A solvent can only hold so much before it reaches saturation. When a warm soda goes flat, it's because the liquid solvent can no longer hold on to the dissolved carbon dioxide gas, allowing it to escape into the air as fizz. By tracking these three variables, physical state, chemical polarity, and particle size, you can identify how any given piece of matter is assembled. The next time you sit down for a meal or pour yourself a drink, take a closer look. See if you can deduce whether you're about to consume a molecular solution, a heavy suspension, or a clever colloidal trick.